Hi everyone, Katie here. This is lecture 5 in the chemical oceanography module. Today we're going to talk about classifying elements. So this is a sort of approach to understanding the importance of different chemicals in the ocean, and this is known as element classification. So chemicals in seawater, so any element in seawater, can be classified into 4 groups. And the way we do this classification is essentially based on what their concentration distributions look like with depth. So those depth profiles that we looked at for nutrients. We also looked at depth profiles for temperature and salinity and density and all those things. So this is now depth profiles of elements. And depending on the shape of that depth profile, they're classified as conservative elements, bioactive elements, which are sometimes referred to as nutrient-like, adsorbed elements, which are sometimes referred to as scavenged, and gases. So this here is a sort of cool view of the periodic table from an oceanic perspective. So it looks like the periodic table you're sort of familiar with. But what they've done is they've tried to indicate for each of these elements whether it fits into the bioactive, conservative, adsorbed, or gases section. And you see for some elements there's no data, like for a lot of the actinides and lanthanides, they're things that just don't lend themselves to being measured in the ocean, or those types of elements that are short-lived experimental type things. So if we start by looking at, let's say, the gases, they have this sort of striping to them. You can see the noble gases on the right-hand side. And then oxygen and nitrogen are also present as gases, as O2 and N2. And then the ones you're probably more familiar with, the bioactive ones, have the sort of normal black border. The conservative elements have the darker border. And then the adsorbed one are the gray shading. So you can notice the adsorbed one, that's pretty much refers to metals, have that adsorbed or scavenged profile. The conservative ones, you can see there's some overlap with the major ions in the ocean. And there's actually a lot of bioactive elements in the ocean. Lots of things are needed for production and for biological activity to happen, not just nitrogen and phosphorus, but it's all the trace elements as well. So the first element classification is conservative elements. And so these are things in seawater that have a constant concentration to salinity ratio. Doesn't mean they have one concentration over the whole global ocean, but it means that the ratio of these elements to salinity stays constant. And what that means is for these elements, that their concentration is not really affected by anything other than precipitation and evaporation. So basically, they act like salinity. They're affected by the things that affect salinity. And these elements can be high in concentration or relatively low in concentration. It's not necessarily about whether there's a lot of it or a little bit, but how unreactive is it from a biological and chemical perspective? It's the way it behaves, not necessarily whether there's a lot or a little. And so most of the major ions are conservative. And if you remember back to when we talked about the law of constant proportions with the 6 major ions and why we could use, for example, you can measure chlorinity and calculate total salinity. It has to do with the fact that the major ions are present in set ratios. And so you can see this table here shows the major ions in surface seawater, or the major ions in seawater at a set salinity. And most of these species have a conservative distribution. Exceptions, of course, being bicarbonate and carbonate, and strontium being an exception. But the rest of them essentially behave conservatively. And so when we think of salinity, you might just think salt, so it's sodium chloride, but it's actually these other major ions as well. And so here is an example of 2 depth profiles of conservative elements. On the left, you can see sodium, and this is the concentration of sodium with depth for the Pacific and the Atlantic. And you can see just by looking at the scale how narrow this range is, right? For the most part, the concentration of sodium is relatively constant. You've got pretty much a straight line here with a minimum deviation. So that might be expected because we know sodium is one of the major ions. But calcium, another major ion, but not something that you think of as a salt per se, also has essentially a straight line distribution. And again, if you look at this axis here, 10 to 10.5 millimole per kilogram is the concentration axis. That's a really narrow distribution. So you can be like, oh, there's variability, but I mean, come on, 10.25 to 10.26 maybe. This is essentially a straight line distribution. So regardless of depth, what you're seeing here is the typical depth profile for a conservative element. It's essentially a straight line. Okay, the second element classification is the bioactive elements, or the nutrient-like elements, and by far there's the most of these of any of the classifications. And the bioactive elements are where you have very low concentrations at the surface, which we also refer to as surface water depletion, and higher concentrations at depth. And we also refer to this as deep water enrichment. And if you remember from the nutrient lecture, this profile is driven by consumption of the nutrient in the euphotic zone. So consumption meaning the biological activity, so phytoplankton use it to grow. They also need to be in the euphotic zone, meaning they need light. And so the concentration goes down because it's being consumed. And then the element is released at depth because that biological material that grew in the surface ends up dying, and then it sinks and it gets degraded. And other terms we use to refer to that degradation are remineralization, or we say it's respired. And so you end up with the concentrations being much higher at depth. And this is true for macronutrients and micronutrients. And if we look here, these are examples of bioactive element depth profiles or nutrient-like depth profiles. You can see for silicate, essentially goes to 0 at the surface because diatoms need silicate to grow. And then you see once you get below about 1 kilometer, maybe 2 kilometers, that you end up with this remineralization profile where concentrations are much higher at depth. Iron is very low in concentration, so that's nanomolar, 10 to the minus 9 moles per liter. And you can see here 0 to 0.2, 0.4, but essentially the profile itself, even though the concentrations are very low as compared to silicate or nitrate or something, iron is a micronutrient. And so it's consumed at the surface and then remineralized at depth. Zinc is the same. I don't know why that's sort of on top. So this is zinc, also a very important trace metal that's needed for growth. Cadmium here on the bottom left, you can see essentially the same thing. Again, very low in concentration, but essentially goes to 0 at the surface and then has a remineralization signal at depth where it's much higher in concentration. You also see, as you would expect, that the Pacific deep concentrations are always greater than the Atlantic deep concentrations. And this connects to what we were saying with the circulation, where the waters, as it's moving along the deep ocean and it's collecting the products of this remineralization, it starts in the Atlantic and it eventually makes its way to the Pacific. So by the time it gets to the Pacific, it's accumulated a lot more. Another way with trace metals that we can confirm they have a nutrient-like profile is you can compare for the same water, you can measure these trace metals as compared to something like inorganic phosphorus or nitrogen or nitrate, which we know are the two biggest major nutrients needed. And you can see in the bottom right here, if you do a scatter plot of phosphate concentrations versus cadmium concentrations, that there's this really strong relationship between the two, which suggests that cadmium is acting like a nutrient. Here's another examples, the ones we're used to seeing, phosphate here and nitrate here, where concentrations go to 0 at the surface because they're being consumed. And then at depth, you have this remineralization signal. And then there's silicate, and then TDIC, that's total dissolved inorganic carbon. It's just showing, so that's the other thing you need for photosynthesis to happen. Okay, the third classification is adsorbed elements, which are also known as scavenged elements. And the depth profiles of adsorbed elements are the opposite of the bioactive. So meaning that they have higher concentrations in the surface waters and lower concentrations at depth. And the reason for this is that these tend to be trace metals that are not needed for biology. So what ends up happening is you have a surface ocean enrichment. So they're high in concentration at the surface because these trace metals usually arrive in the ocean as a result of dust deposition. So they move through, so they're, let's say, soils or metals that get picked up on land and then the dust and the winds carry them out to the ocean, and they're deposited on the surface ocean. And so their concentration in the surface is high. And then as they sink through the ocean, these elements are adsorbed to particles, so they stick to particles. And so if you look at the dissolved concentration in the surface ocean, it gets lower and lower at depth, and that's because these elements are sticking to the particles. These adsorbed elements are also typically quite low in concentration. So if you look here, these are some example profiles. On the left, we've got lead. You can see higher in the surface waters, and then the concentrations go down with depth. And where it's also the reverse, in that you have higher concentrations in the Atlantic than in the Pacific. And it's for the same rationale as the nutrient-like ones. So you end up with these elements, they start sticking to particles. And in the Atlantic, that water is still very relatively young. And as it moves through the Pacific, more of the material has been stuck to particles. And so more of it's been removed, which means you have a lower concentration in the Pacific. Manganese and aluminum are sort of, they act like adsorbed elements. There's a little bit more complicated stuff going on with aluminum, but you can sort of see here and get the gist. The last classification are gases. And gases get their own classification because to be conservative as a gas means something slightly different. So dissolved gases in the ocean can be chemically inert. Argon's a good example of that, or they can be bioactive, oxygen and CO2. In this case, a conservative behavior with gases doesn't mean that the concentrations are constant, but it means that they remain at equilibrium with the atmosphere. Okay, so it's not a constant ratio with salinity, it remains at equilibrium. And so argon has no biological or chemical process that acts on it. And when you look at this profile, you might think, well, gee, that looks like a nutrient profile, and it does. But remember that cold water holds more gas. And so these deep waters are colder than these shallow waters. And so argon is at equilibrium through the whole process. But its concentration will vary with depth because of variations in temperature and salinity. And so the shape of this profile is actually a conservative gas profile. And this variation is solely driven by temperature and salinity and the impact that temperature and salinity have on solubility and the fact that these colder deep waters can hold more gas. And so that's why gases get their own sort of little classification here. So that's it. Just a short little intro to this idea of thinking about different depth profiles. It's also good to start thinking about how you describe depth profiles, so sort of what's controlling the distribution of various species in the ocean. And so next up, we'll get into